Hey, what's up, Chem Peeps? Mr. Boylan here. What in the heck are we gonna do in this vid? We are going to interpret acid-base titration data. As always, taking a quick moment to break it down, you want to be able to interpret an acid-base titration curve for a strong combination to explain the relative concentrations of each thing along the curve, and then use that information to calculate the pH at any point throughout your titration. All right, so as you take a look at your screen in your notes, the first thing I'm gonna do is just walk you through a titration. And as I do that, I want you to focus on what's going on in the beaker as we do that. So our analyte in this case is a strong acid. And I can tell that's a strong acid because it's completely ionized in solution. I don't have any original acid molecules. As I look at my initial pH, it's a really acidic pH, which makes a lot of sense for a strong acid. The titration we're going to perform is going to be between that strong acid and a really strong base, sodium hydroxide. And I've included both the molecular equation and the net ionic equation. Notice that in this case, the conjugate base ion that forms is going to be part of this neutral salt. And because it's a neutral salt, and this conjugate base isn't contributing to the pH, it's grayed out. It's just a spectator, not important for our pH calculations. All right, let's start dropping in the base. As I add strong base, notice that I use up some hydronium ion to form water. Saying goodbye to that hydronium ion. Notice that as the hydronium ion concentration decreases, the pH begins to creep up. Still very acidic because I still have a lot of hydronium ion in solution. Let's add some more strong base. Oh, goodbye hydronium ion. Continues to get used up. Let's add some more. Oh my goodness. At this point, I've used up half of the strong acid that was originally in my solution. Still very acidic solution, still a bunch of hydronium that's left over. Let's add some more. Oh, neutralization. Adios hydronium. Let's keep neutralizing. Whew. Again, we're still along this range here where we've started to add some of our strong base, neutralizing some of that strong acid. But once we've neutralized it all, boom, we've hit our equivalence point. Notice a huge jump in our pH. We no longer have any hydronium ion floating around. We've neutralized it all with our strong base, with our hydroxide ion. All that we see in solution is water and our salt, but it's a neutral salt. These are just spectator ions sort of floating around in the background, not really contributing at all to the pH of our solution. If we keep going though, we jump up in pH once again because now we've got excess hydroxide ion and therefore our pH is very basic. Okay, so now I want to step back and work through that titration again, but I want you to think about how we would calculate the pH throughout the curve. Now that we know sort of what's going on in the beaker as we perform the titration. So initially, we've got a strong acid, which completely ionizes in solution. So if you want to know the pH initially, well, if you know the initial concentration of that strong acid, you know the concentration of hydronium ion. They're going to be the same because it's a strong acid. Therefore, just plug that concentration into your formula for pH, negative log that sucker, and bam, you've got your initial pH. However, as we start adding in the strong base, it's important to know that it's still just a strong acid calculation, but some of that strong acid has been neutralized. So the moles of hydronium is going to have decreased slightly and your volume is going to have increased slightly, your total volume, because you're adding sodium hydroxide to that initial beaker. Therefore, your concentration of hydronium ion is going to decrease slightly. Still very acidic because there's still a lot of excess hydronium, but still just a strong acid calculation. Negative log that new hydronium ion concentration. As you keep going, notice that your hydronium ion concentration continues to decrease as we continue to neutralize it, and therefore the pH will continue to increase. Still, however, it's a very acidic solution because I've got lots of hydronium ion left. Again, as I keep going, that process continues as we neutralize more and more of our strong acid until, boom, we reach our equivalence point. Here, all of the strong acid has been consumed in a perfect stoichiometric amount with our strong base. We've got a neutral salt solution. Neither of the ions of our salt are contributing to the pH. Therefore, the only thing in solution that's contributing to the pH of our solution at this point is water. And water is mostly water. There will be some hydronium and hydroxide ions from the autoionization of water, but a really small concentration, 1 × 10⁻⁷ molar, which means that the pH of our solution at the equivalence point is 7 for a strong acid and strong base. But what happens when you go past the equivalence point? Why did we see that huge jump in pH? Because now we've got excess hydroxide ion. So to determine the pH at this point, what you need to do is determine how much excess you've added of your hydroxide ion, determine the total new volume. Remember, as you add more and more sodium hydroxide, your volume continues to increase. And then of course, just be careful that you're working with hydroxide ion and not hydronium ion. So you're solving many times for POH, and the question will be asking for pH. So you might just have an extra step to do. All right, that does it for this vid. If you need to, I've made an example where I work through the specific calculations along a titration curve. And if you're confused about what was in this video, it might be helpful to go ahead and watch that one as well. Have a fantastic day.